Hi everyone, welcome back to my channel. I'm Anish and today we will start with the lecture 3A of this cache memory chapter. So today we will discuss more about cache mapping techniques. So in previous lecture we discussed about direct mapping techniques, we did few questions. So today we will continue our discussion with direct mapping technique and more mapping techniques. Also we will understand how does a cache hit and cache miss works, how does the block replacement takes place. Before starting, in the previous lecture I made a blunder. Okay, that was the last question. This last question was a blunder, that here, right, this was supposed to be 4, so I should have written here 0 1 0 0, but instead of that I had written 1 0 0 0. So that was my blunder. Okay, so there was a bit swap. Basically the bits should have been swapped, so I have swapped in the notes. So in the notes you will get the corrected one only. And I forgot to mention one thing. If they would have asked in binary, you would have written like this. If they would have asked in hex, so you have to convert this into hex. So basic understanding is you already know how to convert from binary to hex. That is the basic understanding. Okay, so yeah, that was my blunder. I have written the same thing only. Here I have made a mistake. I'm sorry. So if you have forgiven me, make sure to comment below that you have forgiven me. It's okay, it's okay, you can make blunders. Okay, small blunders, not large ones, small blunders. Okay, so yeah, let's start with one understanding of direct mapping technique, and then we will see why we required other mapping techniques. Okay, what was the problem with this mapping technique? So let's take an example. So currently my number of cache blocks is 8. Okay, and memory has total of 32 blocks. Cache memory has 8 blocks, memory has 32 blocks. Okay, so the memory address is divided into 3 fields. So memory address can be divided into 3 fields, that is tag, byte offset, cache memory blocks. Cache memory blocks can be 0 to 7. So what is the size of the number of bits of the cache memory block? Number of bits of the cache memory block will be 3. Okay, what will be the size of the main memory address size? Now they have not given me, yeah, okay, they have given me block size. So main memory total has uh, 32 into 4, that is, sorry, this will be 32 into 4, right? Cache size is 32 bytes, main memory size will be 32 into 4, that is 128. So main memory size will be 128 bytes. What is the size then? What is the number of bits? Number of bits will be 7. So main memory has 7 bits. We'll write here 7 bits. And my byte, what is the byte offset? Byte offset will be this will be 4 bytes, right? So this will be log of 2. Yeah, this will be 2 bytes, 2 bits. Okay, so if I combine this 2 bits and 3, what is the tag size? Tag size will be 2 bits. Tag size will be 2 bits. That will be the tag size. Tag size will be 2 bits. Okay, so now yeah, so these are all the things basically, but these are actually not required. What is the main point of explanation is here. So let's say CPU request a block 2 from the main memory. CPU always request from the main memory, and assumption is initially the cache memory is empty. So initially as the cache memory is empty, so whenever the CPU will request for the block 2, what will happen? It will be a cache miss or cache hit. It will be a cache miss. Okay, so this will be a cache miss. If the CPU request for the block 2, it will be a cache miss. Okay, because initially cache is empty. Initially cache is empty. So in the block, like where will I go? CPU is requesting for block 2. Basically it will be stored in block 2 only, right? So if it's a cache miss, now block 2 will be stored with the like block 2 of, sorry, cache memory block 2 will be stored with a block 2 of main memory. So here, like in block 2 only, 2 10 18 these can be there, right? Why? How 2 10 18? Basically I'm doing whatever the number mod 8. If I do mod 8, it will give me 2, so that will be the block number. So this we have already discussed in the previous lectures. So okay, now 2 is there. Now next, right, CPU request for 18. Now if CPU request for 18, where in which block number I will go to check this in the cache memory? 18 mod 8. What is 18 mod 8? 18 mod 8, if you do, it will be equals to 2. So again, the cache controller will go to the block number 2 and check, match the tags. But cache controller sees that currently I have block number 2 of main memory. I don't have block number 18. So of course it is a miss. It is again a miss, right? It is again a miss here. Again a miss. So again I will replace this 2 to 18. Again in the next request, again the CPU request for block number 2. So again it is a miss, right? Again it is a miss. Why it is a miss again? Because now again I will go to block number 2, but I will see currently I don't have 18. I have 2. So I had to actually, but I replaced it because the two blocks of the main memory were competing for the main block number, like same block number in the cache memory. The two blocks in the cache memory, sorry, the two blocks in the main memory were competing for the same block number in the cache memory. So again I will replace this by 2, and this will go on. Again I request for 18. So again there will be a miss. Again it will be replaced by 18. Again I will request for 2. Again there will be a miss, and this will keep on happening, right? So actually there is no advantage of having the cache memory. Actually, if you observe, there is no advantage of having the cache memory. Even though I'm frequently accessing the blocks, but still I'm not getting any advantage. I have to go to the main memory every time. So that is what is written over here, that CPU request for these blocks, cache miss occurs each time as block 2 and block 8 replace each other. Basically, why? Because the both blocks compete for same cache memory block, both main memory blocks. Okay, both memory blocks compete for the same cache memory block. So that's why there is happening like frequent, if I am accessing it frequently, still I am missing it, due to which cache miss is occurring, even though there is frequent access. So even though there is frequent access, still cache miss are occurring. Okay, still cache miss are occurring. So like it's still it's not of no use. So we had to think of something else. So what we thought is we will use a set associative mapping. We will use set associative mapping. What is set associative mapping? I will explain. So let's take example of two-way set associative mapped cache. So now each set, like this will not be a block anymore, this will be set. So these will be called, these will be not the block numbers, this will be called the index slash set. Index, these are called index slash set. So what we did, right, previously my cache memory had the capacity of storing 8 blocks, correct? Now also if you see, my cache memory has the capacity of storing 8 blocks. That is true. Now also cache memory has capacity of storing 8 blocks, because each box here will contain a block. Each box here will contain a block. That's it. But what is the difference? Same. I can still store here 8 blocks. 1, 2, 3, 4, 5, 6, 7, 8. Here also I was able to store 8 blocks. But now as I have index here, so for a single index, 2 blocks can stay. What do I mean? So let's take the same example. Let's take the same example, 218, 218. Okay. So these are the index now, right? This is not the block number anymore. This is the index. So now if I do 18 mod 4, it will be 18 mod 4, the number of index, right? Or the number of set. So 18 mod, sorry, 2 mod 4 will be what? 2. 18 mod 4 will be what? 2. Now they will not compete because 2 has 2 slots. 2 has 2 slots. So even if I fill up the first slot with 2, the second slot can be filled with 18. Got it? Even if the first slot is filled by 2, the second slot will be filled by 18. So still I have one more space left for filling the same set. Okay. So if you observe here, like what we are doing, this 2 is the 2 mod 4, that is 2, then 6 mod 4 is 66, then sorry, 6 mod 4 is 2, 10 mod 4 is 2, 14 mod 4 is 2, 18 mod 4 is 2, and it will go on like this. Okay, it will go on like this. Okay, and these are my sets basically. I hope we got this one. So what is the difference? What is the difference? This is the example basically, that what we did, we changed the organization. So what we did in set associative mapping, we change organization. What do I mean by organization? Basically how blocks are organized in cache memory. That is what we did, right? So cache memory size is same, just how they are organized I am changing it. Okay, organized in cache memory. Okay, so like what is the thing is, this can go for 2-way set associative, this can go for 4-way set associative, and like we can increase it even more. So currently you are seeing an example of 2-way set associative. In this example, each set or index will have 2 blocks. If I have 4-way set associative, 4-way also exist, 8-way also exist, like it will go on, right? 4-way, 8-way. Okay, it will go on. If I increase it 4-way, 8-way, basically I will have 8 blocks in the same set. I will have 2 blocks in the same set, and it will keep on go on. Okay, so what is the main point? Now I have main memory address. So previously what we knew is my main memory address, like for direct cache mapping, my main memory address had 3 components. One was the tag component, one was the cache memory block number, another one was the byte offset. Correct? So one was the tag, this was the cache memory block number, and this is the byte offset. Okay, so I had 3 fields. So now the cache memory block number will be changed. Byte offset has not changed, right? What have we done? Basically previously I had 8 blocks, now I have 4 blocks. So 4 blocks, not 4 blocks actually. Previously I had 8 blocks, now also I have 8 blocks, but now I am arranging them differently. Now they are not arranged in a single column. Now I have 2 columns now. So basically this cache memory block number will be changed to index or set number, set offset, index or set offset. Okay, so how many number of indexes I have? So how do I calculate the number of indexes? So total number of blocks, right? Whatever are the total number of blocks in the cache, divide by its associativity. If it's a 2-way associative, cache, then I will divide by 2. That means 8 divided by 2 is 4, which is 4 I am seeing here, right? Index is 4. If it is 4 way associative, then it will be 8 divided by 4, that is 2. So I will have only 2 indexes where each index will contain 4 blocks. So basically my number of indexes in associative mapping. Number of indexes in associative mapping will be the total number of blocks in cache memory divided by the uh, set associativity, right? Number of sets or associativity. So I can write either associativity or number of sets. So I have to get the space. Sorry for the crying noise. I'm really sorry. This baby is crying since yesterday. I don't have any option. So uh, like what I can do, what I can do is this one. Okay, now what is the set number in which a particular block will be placed? So how do I calculate the set number? It is simply equals to the main memory block number mod of the number of sets. So main memory block number, let's say, is 4 and number of sets is 4. So 4 mod 4 will be 0. So hence 4 is placed in set 0. Main memory block number is 8. 8 mod 4 is again 0. Hence it is placed in set 0. Like this you can do. So the set number where the block will be placed. Set number number of cache memory set number of cache memory will be equals to main memory block number, main memory block number mod of the total number of sets. Okay, understand this conceptually how the formula is coming. Again I am telling you, don't mug this one up. Okay, understand it conceptually. Okay, how do I, so what we can do is we can So yeah, I hope you have understood this basic thing now, right? At this point of time, if I, for the same scenario, that I have block 2 can reside here and block 18 can reside here. Now they don't need to compete for the same place. Now, and another thing is there will be tax associated with them, so they will have different tax. Okay, so don't worry. So I will write here, these will have different tax, both of them will have different tax, both of them will have different tax, and they don't need to compete for same cache memory block, because now I have two space, right? Two spaces, so these won't have to compete for the same cache memory block. So yeah, that was the advantage of this set associativity, right? So yeah, now your main memory address has changed. So now your main memory address, this is my main memory address. The way I am representing my main memory address has changed. Main memory address. Okay, so main memory address, here I have tag, here I have set, here I have byte order. Okay, so now each block will have two tags. Two-way set associativity means I will have two blocks and both of the blocks will have two tags. This will be for the first one and this will be for the second one. Okay, so of course, first, depending on the set number, like you have got the main memory address, right? This is my main memory address. Okay, it is already written in the bottom. You have got the main memory address. So you've got the main memory address, byte offset. You will not check first. First, what is your task? First, your task of the cache controller is to check the set number. So first we will check this one. Okay, first we will check this one. This one will be the first priority. So first I will check the set number and then I will go to that particular set. Let's say the set number was 2, because I will do the mod of 4 with that. Whatever mod value I will get, that I will go, right? Set number I will calculate from here and then I will go here. Then I will compare the tags. So then the second thing is I will compare tags. Okay, now I will compare both the tags. Basically, there can be three cases. This tag, right? I will compare both the tags here. These two will have their own tags, right? I will compare this tag with this one as well and this one as well. I will compare both the tags. Compare both the tags. Why both the tags? Tag is a unique identity, right? Tag is a unique identity. If you see here in the direct mapped cache, if I go back, let's go back with very starting, right? Where was the tag? So where was the tag? Yeah, tag was here. So if we see here, what is the tag here? So the tag here, right, is always the starting bit, correct? So if it is block 000, then I just, these two are my cache memory block number and first number is the tag. If I want to have block again next time when I will get block 00, it will be here, correct? It will be here. Here if I see, tag has changed. So tag will always be a unique number. Again next time when I will get block 00, again the tag will be changed. So tag will be always a unique number. So each block will have a tag always. That is always the case. So I will write here, the tag is always a unique number. important point, that my tag always a unique number. So I will compare both the tags of both the blocks and I will check, like there can be three cases. Either one condition, first tag matching is true, second one is false, or either if it is false true, like if first tag is not matching, second tag is matching, or both are false. You will say, sir, what if both are true? Both true is not possible. Both true, not possible. Why it is not possible? Why it is not possible? It is not possible. It is not possible because tag is a unique number. So whatever tag I got from this main memory address, it cannot be like both have the same tags. Not possible, right? That means both have the same content, and that is not possible. If already I have block B1, it's not like I will again store here block B1, correct? I will only store block B1 here once. If block B1 is already present, I will not store again block B1, right? That is not possible. So not possible because tag number will be unique and a block number will be stored only in a single block, right? It will not be repeated. Okay, so that's why these three cases are possible. So if these three cases are possible, these two cases are the case for which I will have a cache hit, because either the first one is true, that means first one matched is tag, that means my required data is in the first one, or the second one, in the second case, the second one matched the tag, that means my second block is the required data. So in these cases I will have a cache hit, and in the last case I will have a cache miss. Okay, cache miss. This will be cache miss. So just reiterating it, why 2f is not possible, because if, for example, if I already have, if I already have, if I already have a certain block in cache memory, then automatically when the CPU will request for that block, right, there will be a hit always, right? There will be a hit. So why will I bring that block into the cache memory again? Certain block in cache memory, why will I bring the block again? Why will I bring the block again into the cache memory? There is no point in bringing the cache memory again, right? So this was the important point, and important crux is that if any one of the comparison, like in this case there it was two-way set associative, let's say I will have 4. So out of the 4, if any one of them, any one of the comparison is true, that means it is a hit, otherwise it is a miss. That is the main conclusion that I want to take away from this particular discussion. So if any one of the comparisons are true, then if any one of the comparisons are true, then it will be a cache hit, then it will be a cache hit, otherwise it will be a cache miss. Okay, if it is like, if none of them are true, that means it is false, that means it will be a cache miss. So that was the key point, key takeaway that I wanted to give in this discussion. So let's do one example and we will understand this even better. So let me copy this blog. Okay, copy this thing here and let's do an example. So here if I see, given that the main memory address size is 30 bits, so main memory has 30 bits, directly they have given me. Cache memory size is 64 kilobytes, block size is 16 bytes. So block size is 16 bytes. What is the byte order or byte offset? Byte offset will be log of 16, that is 4 bits. So byte offset will be 4 bits. What about the set associativity? They have told me it is 4-way set associative. It is 4-way set associative. So first of all, I have to find out the number of cache memory blocks. Number of cache memory blocks. So number of cache memory blocks will be equals to what? The total cache memory size divided by the block size. So 64 kilobytes divided by 16 bytes. So it will be 2 raised to power, like it is 4, right? It is 4k. 4k. 4k is 2 raised to power 2 into 2 raised to power 10. So it will be 2 raised to power 12. 2 raised to power 12 is the number of blocks, cache memory blocks. So number of cache memory blocks is 2 raised to power 12 and it is a 4-way set associative. So in each set there will be 4 blocks. So number of sets or index will be equals to number of sets or index will be equals to 2 raised to power 12 divided by the 2 raised to power 2. So it will be 2 raised to power 10. Okay, so yeah, number of set will be 2 raised to power 10. This will be the total number of sets. So how many bits do I require for number of sets? How many bits? It will be log of 2 raised to power 10, that is the bits for number of set. So bits for number of sets will be 10 bits. So number of sets will be of 10 bits. So this will be 10 bits. So this will change the color, 10 bits. So what will be the total tag bits? Main memory is total 30 bits. So tag bits, right? Tag bits will be the remaining ones. Okay. So if you observe, the tag bit size has increased. If you observe, the tag bit size has increased. So that is the disadvantage of this particular way of mapping. The size of tag bit will increase, and if the tag bit size increase, the tag directory size will increase. So I have to store more metadata. So I need a larger cache memory, because of course I have to store the tag directory as well, right? So all that information about the tag. So size of tag bit increases. Okay. So if it was direct mapping, then the size of tag directory would have not be this much. I will show you with comparison. If it was direct mapping, I would have I will show you the comparison as well. But let's first calculate the tag bits with set associative mapping. So tag bits will be total number of bits in the main memory, that is 30, minus the number of tag bits, sorry, minus the number of set bits and the byte order bits. So it will be 10 plus 14, 10 plus 4, so it will be 16 bits. Okay, so 16 bits will be the answer. 16 bits will be the answer of this particular question. Got it? So For this particular question, 16 bits will be the answer. That is the tag bits. What is the size of the tag directory? Again, size of the tag directory is very, very simple, right? How do you calculate the size of the tag directory? It is equal to size of tag directory. This is the first one. This is the second one. Tag directory will be like how many do I need to store? It is equals to the number of blocks. It will be always equals to number of blocks, because if you see, although I had 4 sets here, for each set I was storing 2 tags. For each set I was storing 2 tags. So total number of tags is still the same. It is still 8 here, right? Because I have 4 sets and each set has 2 tags. So 4 into 2 is 8. In the first case as well, for direct map, if you see for direct map, here also if you see for each block I will have a tag. But here for each set I had 2 tags. So number of tags do not change. So that is also another important point to note here. Like these are all key points. Key points. This is also another key point. The total number of tags does not change if it is direct mapping or set associative mapping. So it does not matter, the tag number of tags will not change. So what will be the size of the tag directory? Size of tag directory will be size of each tag bits, that is 16 bits, into the total number of tags, that is total number of blocks of the cache memory. So number of blocks of the cache memory. So as it does not change, right? This will not change. Number of blocks in cache memory. So this will be equals to 16 into number of blocks is number of blocks. How many number of blocks do I have? Number of blocks is I guess 2 raised to the power 12 here, right? We have calculated. So it will be 2 raised to the power 12. So if you want to write this in terms of bytes, you can write. So this will be 2 into, so this will be 8 kilobytes. 8 kilobytes. This will be the size of the tag directory. Okay. Now let's check if I would have chosen a direct mapping. So let's check for direct mapping. If I would have not chosen two-way set associative, what would have changed? So yes, it is advantageous. This two-way set associative is advantageous because now 2 blocks of same set number do not have to compete for only a single storage. They can be stored in 2 different blocks in the same set. But if I would have chosen a direct map, so obviously byte offset will be same. Byte offset will not change. The set will change. Set will change, right? So instead of set, I will have a, here this will be cache memory block number. Cache memory block number. Okay. So this will be cache memory block number. So now then this will be not 10 bits anymore, because cache memory number of blocks in the cache memory is 2 raised to power 12. So this will be 12 bits. So my tag bit size will be what? Now my tag bit size, right? Tag bits will reduce. It will be now 30 minus 12 plus 4. This will be equals to 14 bits. Okay, so this is my tag bits basically. So now, okay, so that is done. These are my tag bits. So now what is the tag directory size? If I see the tag directory size, the tag directory size will be 2 raised to power like what are the total number of cache memory blocks? 2 raised to power 12 into the size of each bits, that is 14. So this will be equals to, if I calculate, this will be equals to, if I divide by 2 cube, so this will be 7.5 kilobytes. If you see here, this was 8 kilobytes, this is 7.5 kilobytes, and actually it is considerable. Why? Because this is the cache memory storage. So if it is a cache memory storage, then obviously every bit counts, every single bit counts there. Okay, so like why? Let me show you the task manager, right? I have shown you previously as well. So let us go in the task manager. If I show you in the here in the CPU, if you see, like it's only 384 kilobytes. Okay, L1 cache, L2 cache is higher, L3 cache is higher. Okay, so I hope you can understand, right? I hope you can understand, like every byte counts here. So even if I can save some storage, that is good. So of course there is an advantage of set associative, and this is the disadvantage. So important conclusion is, as the number of sets will go up, hence the tag directory size will also go up. But yes, that is also true that this is the disadvantage. An advantage is what? Advantage is that now same blocks will not have to compete for the single storage space. So like basically blocks will not have to compete against each other. Two blocks can be there. If I want, I can keep 4 blocks. Okay, there are multiple ways, multiple options. Okay, so I hope you have got this point, that what is the advantage, what is the disadvantage, right? So like here, now let's come to the final one, that is fully associative mapping. So let's slowly keep on increasing our associative. Fully means it is full. Okay, I will explain what does full mean. So here, when I had direct mapped, if I have direct mapped, then if I just write this, copy this thing, okay, here, copy this thing. If I have direct map, and I don't know what is the block size and all those things, just hypothetically, let's assume few things. Okay, I will assume few things. I will first of all make this smaller. Okay, so hypothetically, if I assume my currently how many cache memory blocks I have? 8. So this will be, what will be the bit number of cache memory block number? It will be 3, right? I will require 3 bits. And for tag, let's assume it is x. Okay, for tag, let's assume it is x. Now if I come to the two-way set map, then again I will copy this one. Now the cache memory block number will be changed into set number. Now if I compare the two-way set map, so here what will happen is that byte offset I don't care, So now the set will be what? Now I have it is two-way set map. So it is set. How many bits do I require? 2. Previously I required 3. Now I will require 2 because I have 4 sets here. So it will only be 2. What about tag? Tag will become from x to x plus 1. Tag will become from x to x plus 1. Okay, and it is, if it is 4-way set map. If it is 4-way set map, then my set will become 1 and tag will become x plus 2. Why? Only I need 1 bit to represent 0 and 1, and each set contains 4 blocks. If I increase it even further, if I make it 8-way set mapped, how many bits do I require to represent 8-way set map? It is only, I don't require any bits, right? So I have only a single set. So I don't require any bits for set. So automatically the set offset will be 0. So automatically the set offset will go 0. Okay, this will be byte order. Automatically the set offset will go 0. Okay, and this will be x plus 3. So when my set offset is 0, that means it is fully associative. I don't have any space for set. I don't need any space for set. The whole main memory address can be converted into 2 fields. One will be for the tag field, other one will be for the byte offset. That's it. So set can go away. So there is no set field. One is for the tag field, other one is for the byte offset. Okay. So you don't need to apply any formula. No need to apply any formula. Of course, the tag size, tag data size is getting increased. And what is the advantage of fully associative? Not much actually, not much. Basically, blocks don't have to compute, but I don't feel like this is too much advantageous. We will see example as well with comparison. But this one is the hybrid solution is the best one. This is the best. 2-way or 4-way are the best ones. Okay. So here, right, you don't need to use any formula. So I will write here, no need to use any formula. And anyways, I have to told you, no need to remember the formula, just understand the concepts. So no need to use any formula. Just directly calculate the byte offset, and from byte offset then you subtract the main memory and you will get the number of tag bits. Of course, as that tag bits are increasing, tag data size will keep on increasing. Tag bits increase, tag data size will keep on increasing. So why my tag data size, if I say that my tag directory size my tag data size will be proportional to the tag bits, number of tag bits. Okay, so tag data size will be proportional to the number of tag bits. Now let's do an example. From there we will understand this even better. So given the following parameters, my main memory address size is 32 bits, cache memory size is 128 kilobytes, block size is 32 bytes. So what is the byte offset? So always your first intention should be to calculate the byte offset. Okay, so byte offset will be log base 2 32, so it will be 5 bits. Byte offset will be 5 bits. What is the cache memory size? So the cache memory size, I don't need to find out. I need to find out the number of cache memory blocks. This will be, just hold on. Are my assignment questions there? Yeah, assignment questions are there. Okay, fine. So number of cache memory blocks will be equals to the total cache memory size 8 kilobytes divided by the 32 bytes. So this will be 4 kilo. So it will be like basically 2 raised to power 12 again. So total number of blocks is 2 raised to power 12. So how many bits do I require That I will come to. That I will come to. So main memory size is 32 bits. Okay. So for direct memory cache, what will be the number of tag bits? So for first question, direct mapped cache. So direct cache, for direct mapped cache, basically I know the number of bits for the byte offset, so I will copy this whole thing. For byte offset, for byte offset it will be for byte offset it will be uh, 5 bits. Then cache memory block number, how many bits do I require for cache memory? It will be 12 bits, right? I will require 12 bits. So of course, what will be the tag block, because main memory address has 30 bits. Main memory address has 30 bits. Okay, sorry, not 30, 32 bits. Okay, so number of tag bits, x will be equals to 32 minus 17, so it will be 15 bits. So it will be total of 15 bits. 15 bits will be required for tag in case of direct map. If it is a four-way set associative, right? Four-way set associative cache. If it's a four-way set associative cache, it will be what? It will be equals to like I will just copy this whole thing. Now the cache memory block will change to set number, right? So now this will be set number. So byte offset will be same. Byte offset will not change. It will be 5 bits only. The set number will be what? So number of sets will be equals to number of cache memory blocks, that is 2 raised to power 12, divided by the set like the associative number, set number, that is 4. So it will be 2 raised to power 2, so it will be 2 raised to power 10. So this will be 10 bits, right? Log base of 2 raised to power 10 is 10 bits. So overall it is 32 bits. So overall my tag bits will be equals to what? X will be equals to what? X will be equals to 32 minus 10 plus 5. It will be 17 bits. This will be the tag variety size. And for fully set associativity, fully, third one, fully set associativity, you don't need to calculate anything, right? Fully set associative, you don't need to calculate anything, because you know the set bits will be 0. Number of set bits will be simply 0. Okay, so number of set bits will be set bits will be 0. So byte offset is 5. So x will be the tag bits, that is x, tag bits, that is x, equals to 32 minus 5. So it will be 27. So can you imagine, 27 bits will be given to the tag directory. So what will be the tag directory size? Sorry, tag bits. So what will be the tag directory size? So tag directory size. So this will be 2 raised to power 2 raised to power 12, because this will be same, right? This will be the number of cache memory blocks into whatever that tag bits is. So I will copy this in the other ones as well. So here it will be 2 raised to power 12 into 27 bits. Here it will be here it will be 2 raised to power 12 into 17 bits. Here it will be in direct mapped cache, it will be the lowest. 2 raised to power 12 into 15 bits. So like I hope you can see the tag directory is lower and lower as I reduce the set number, but of course there is a problem of the conflicts. Okay, so now I hope you understand what kind of conflicts I can have. So in the direct memory mapping, I told you that there will be conflicts. So now I hope you understand what do you mean by conflict, like same competing for the same block. So I will write in the key points there that so in direct cache mapping, higher chance of conflict, that is they are competing for the same block, higher chance of conflict. But of course the tag size, directory size is lower, chances of conflict. Okay, but for other kind of mapping the chances of conflict is lower. Chances of conflict is lower, I mean in 4-way set, associative and those things. So it is here basically the comparison I have done. Basically you can go through it. So tag bits will be, as I increase my associativity, tag bits will increase, index bits will again reduce, that is the set bits will be reducing here. Okay, then offset bits will be same, it will not change. Flexibility, it has low flexibility because I have only one block per index. It has higher flexibility, this will have highest flexibility, but of course the tag directory size will be very high, that is not great. Okay, got it. So search complexity is simple here, moderate, all these things. Speed, you can see speed will be fast because only I need to do one tag comparison here, right? I have to do, let's say, 2 tag comparisons or 4 tag comparisons, so it will take time to compare and it will be the slowest because I have to compare all the tags of the cache memory. I have to compare all the tags. It's a very bad idea. Okay, space for tag data, this will be small, this will be medium, this will be large, obviously for obvious reasons. Okay, conflicts, here this will be high, this will be reduced, this will be very high, this will be the lowest cost, this will be the moderate cost, this will be highest, and I hope you now know which one to use, the middle one, right? It's a hybrid mixture. Okay, so these are the few key points that you need to keep in mind, and throughout all of the things the block size will not change, that is the number of bits for block, number of bits, unless specified that they are changing the blocks, number of bits for byte offset will not change. Okay, it will not change. So yeah, that's like you can see, like whatever I have discussed, same is written over here. Okay, according to their space conclusion and all those things. So direct mapping is simple for suitable for simple systems where cost is very important and speed are the priorities, but there will be conflict misses. So but conflict, you don't want conflicts, then you will use the 4-way set associative. Okay, fully associative we really use. Okay, we don't use fully associative because the cost is even higher, and like yes, it eliminates the conflicts, but the time complexity is also very high, right? So that's why. So these are the features basically, whatever I have like told there in the table, the same thing is summarized here. So I want to give you few homeworks so that we will solve all this in the next lecture. So these are the assignment questions, homeworks. Try to solve all these questions, and in the next lecture we will solve all this. Take a screenshot and try it out by yourself. This will not be that difficult, these will be simple questions only. Okay, so yeah, like there are a lot of questions, there are valid bits, everything is there. Okay, a lot of things are there, so try it out on your own, and in the next lecture we will solve all the questions. All these questions we will solve in the next lecture. This one is one of the questions, and this one is the last question, I guess. 24 is the, no, 20, after 24 also we have. So we will solve a lot of questions in the next lecture. Okay, so this is the last question basically. I think, yeah, we end our lecture. So I hope you have enjoyed this lecture. If you did, make sure to hit a like below and share with your friends, and obviously comment down below in the first video of this playlist and also in this video if you are enjoying the particular concepts. I hope you have enjoyed this video. I will see you in the next lecture. Until then, happy learning.